Hi, this is James Courson, CSC480 Assignment 2 submission. Okay, so we're going to get right to it. You run the dance battle. So you can select from the different test cases. We'll run one, and you can see here is the dance moves and the win. And then, like another dance battle, we'll run a second one. Okay, here's the second one. And you can see the play-by-play of the moves being popped. Here is the entire dance battle with the win for Max. Okay, so I modeled this as a problem. Here's my problem class with some problem-specific data here. Brute number of dance moves. This is the moves that are that get used. These are the pre-selected moves that you don't get to choose from in the goal node. And then mapped it to a solution which has the winning number, the and the solution path. And here is the main, which just has the menu. Get the file in. Determine which moves we have to make. Store the moves that are taken and their reverses. Here's where we init. Here's where we set the problem-specific information. Init the start node. Oh, the node, yeah. We also use a node here, which contains, this is the move, and then some other information. We're not actually using all of this. I took out most of the stuff that was unnecessary, that was superfluous from the previous node, the previous assignment node. In general, I tried to reuse what I could from the previous assignment. We also have the base class of search, which has a lot taken out of it. A lot of unnecessary stuff for this actual assignment. But we're using the base class search and we're using the node. So, back to the main. Define our problem, init our start node. We create our agent and we pass the agent the problem. And then ask him to solve it. The agent runs the algorithm, the min-max algorithm here. Once he comes back, he gets the winning number, the depth of the goal node, which is the terminal node of the winner. That will tell you who wins. Kicks it back to the main. This is where the main displays all the information about the winner and the prints the solution. So the agent sets all this stuff up, runs his solve method, which creates the min-max algorithm, and then searches for the winning node. Once it receives the winning node, it just rewinds it to get the path, get it formatted to be displayed properly. So min-max is where we do all the work. Here's the min-max search algorithm. First we set the depth limit that we're going to begin our searching. We're setting it for 2ply, and then you request the optimal move. Once you receive the optimal move, if it's got value, then you add it to the path, reset everything. Well, if it's the leaf, that means you found the terminal node, you return it back. But then you increase the ply, and then you clear everything out. Clear your queue and your the moves taken, the optimal node, and then you enqueue the optimal node that you have received from here. So when we go into our optimal move, we dequeue the first node from the queue. If we're at the current state, that means the queue is empty. Return the null. Check for a duplicate. That's where you check for the move and also its reverse. Actually, the way I modeled it, when you take the move, it stores the reverse as well in the map, which takes the moves. So really, you only have to ever check for if your actual move is in the map, because the duplicate's already stored. If everything is fine, you pop your freshest dance move. Takes the data of the node. This is where you put it in, and also put the reverse in the moves taken. Each of the nodes maintains its own separate copy of the moves taken. That way you can, when you back up the node, go down different paths. Everything is all hunky-dory. Okay, so if the depth limit has been reached, or rather if it hasn't, you expand the children and queue them into the node. Into the queue. If you reach a root node, you evaluate the heuristic that we've used. And here, the heuristic that I used is you take the two moves in the node and you count how many times each of those moves has been used along your path back to the root. And then the idea is the moves that have been used more often are putting you closer to a terminal state, because the number of moves are limited. So here's this is the counter. If you were to set this to false, it would just run regular min-max. Set the optimal node. Check the values for your min and max. Set the optimal node. You know here that you're a leaf node. Set it and then backtrack. Backtracking, when we move back up the tree from a terminal node or from we also backtrack if we reach the depth limit. If we're not the root, then we get our parent. We check the parent's value, and we check the name, whether the parent, whether we are min or max. Here, and that determines which value, the higher or lower value, you pass up to the parent. That becomes the optimal node. In this manner, you push the optimal node up to the top of your selection so that you can choose from the current node. You have to choose from its children to select the most optimal node. Here is where we were to be implementing the alpha-beta pruning. After you, on your way up, as you travel back up, you would prune depending on whether the values in the node required it. But I couldn't get this to work. Once all of the parent node's children are evaluated, then you backtrack up. Here's our expanding, generate the legal moves, generate children from those moves. Generate our children, set all the values, parent name, depth, path cost. Don't actually use the path cost, but I set it anyway. Okay, and yeah, so there you have it. James Courson Assignment 2 submission.